In the previous lecture, you studied the types of numbers in the number systems, some basic properties of integers, and the concept of division algorithm. So in this lecture, I am going to discuss some more problems on division algorithm. Later, I will move to the greatest common divisors. Now let us take a problem. Prove that the square of any integer is either of the form 3k or 3k plus 1. Let us move to solution. If a is an integer, then we have to prove that a square is equal to 3k or a square is equal to 3k plus 1. By division algorithm, every integer a is of the form 3q or 3q plus 1 or 3q plus 2. So in the first case, let us take a is equal to 3q. Let a is equal to 3q, then a square is equal to 3q whole square. That can be written as 9 into q square. So this can be written as 3 into 3q. Now let us consider when a is equal to 3q plus 1, let a is equal to 3 times of q plus 1, then a square is equal to 3 times of q plus 1 whole square, that is equal to 9 into q square plus 6 into q plus 1. So this can be written as, take 3 common in the first two terms, 3 times of 3q, 3 times of q square plus 2q plus 1. So this is equal to 3 times of k plus 1, where k is equal to 3 times of q square plus 2 times of q. Therefore, a square is of the form 3k plus 1. So now in the third case, a can be written as 3q plus 2. Let a is equal to 3q plus 2, then a square is equal to 3 times of q plus 2 whole square. So this is equal to 9 into q square plus 12 times of q plus 4. This is equal to 9 times of q square plus 12 times of q plus 3 plus 1. From the first three terms, we can take a common 3 here. 3 times of 3q square plus 4 times of q plus 1 plus 1. So this is equal to 3 times of k plus 1, where k is equal to 3q square plus 12q plus 1. So therefore a square can be written in the form 3k plus 1. The square of any integer is either of the form 3k or 3k plus 1. Show that any integer is of the form 6k plus 5 is also of the form 3j plus 2, but not conversely. Let us move to solution. Let a is equal to 6k plus 5. This is equal to 3 times of 2k plus 1 plus 2. So this can be done as 3 times of j plus 2, where j is equal to 2k plus 1. So therefore I can write a is equal to 6k plus 5 is also of the form 3j plus 2. Show that the converse is not true. Let 3j plus 2 be an integer. We note that j is either even or odd. Suppose if j is even, that is considered as 2m for some integer m, then 3j plus 2 is equal to 3 times of 2m plus 2, that is equal to 6m plus 2. So this is not of the form 6k plus 5. Suppose if j is equal to 2m plus 1, then 3 times of 2m plus 1 plus 2 is equal to 6m plus 5. But here when j is equal to 2m, 3j plus 2 is not of the form 6m plus 5. Therefore the converse is not true. For example, Let A is equal to 8. So 8 can be written as 3 into 2 plus 2. So is of the form 3j plus 2. So similarly this can be written as 6 into 1 plus 2. So this of the form 6k plus 2, but this is not of the form 6k plus 5. So therefore 3j plus 2 cannot be written as 6k plus 5 form. For j is let us move to the definition of divisibility. An integer a is said to be divisible by an integer b where b is not equal to 0. Symbolically we write b divides a. If there exists an integer q such that a is equal to bq. Suppose a is not divisible by b, then we write b does not divide c. For example, 3 divides 6, so this can be written as 6 is equal to 3 into 2. So 2 divides 10, so this implies 10 can be written as 2 into 5. So now we'll move to the properties of divisibility. For integers a, b and c, the following are true. A divides 0 because so 0 can be written as a into 0, so that is equal to 0. Therefore a divides 0. Divides a because so a is equal to 1 into a, so this implies 1 divides a. And a divides a, so since a is equal to a into 1, so this implies a divides a. So for example, 2 divides 0, 1 divides 2 and 2 divides 2. Let us take second result. A divides 1 if and only if a is equal to plus or minus 1. Third result, if a divides b and c divides d, then ac divides bd. So we'll move to the proof of this. Here A divides B. This implies B can be written as A into K1 for some integer K1 belongs to Z, and C divides D. So this implies D can be written as C into K2, where K2 belongs to the integers. Now multiplication of 1 and 2, 1 into 2 implies B into D can be written as A into K1 into C into K2. So this can be written as AC into K1 into K2. This is equal to AC into K, where K is equal to K1 into K2. So this implies AC divides BD. So this is the proof of the result. Now we take the fourth result. If A divides B and B divides C, then A divides C. Let us move to the proof of this. Here A divides B, so this implies B is equal to A into K1, and B divides C, this implies, so C can be written as B into K2. So this implies, so B is equal to C by K2. So this implies C is equal to A into K1 into K2. Since B is equal to A into K1, so this implies C is equal to A into K, where K is equal to K1 into K2. So this implies A divides C. A divides B and B divides A if and only if A is equal to plus or minus B. So proof of this result is you can try yourself. Let us move to the sixth result. If A divides B and B is not equal to 0, then modulus of A less than or equal to modulus of B. Seventh result, if A divides B and A divides C, then A divides Bx plus Cy for an arbitrary integers x and y. So now we'll move to the proof of the results. Since A divides B, this implies B is equal to A into K1, and A divides C, this implies C is equal to A into K2. So Carter's equation 1 and 2. So multiplying 1 by x plus multiplying equation 2 by y implies bx plus cy is equal to a into k1x plus a into k2y for some integers x and y. So this is equal to a into k1x plus k2 into y. So this is equal to a into k, where k is equal to k1x plus k2y. So this implies a divides bx plus cy, where x and y as an are arbitrary integers. So now we'll move to the definition of greatest common divisor, or correct as highest common factor. Let a and b be given integers. So a and b both not zero. The greatest common divisor of a and b is denoted by GCD of a comma b is the positive integer d satisfying the following. D divides both a and the integers b. Second condition, if c divides a and c divides b, then c is less than or equal to d. Therefore, the positive integer d is the greatest common divisor of a and b. For examples, let a is equal to 4 and b is equal to 6. The divisors of 4 are 1, 2 and 4. Then the divisors of 6 are 1, 2, 3 and 6. Here you can observe that the highest common divisors of both 4 and 6 are the 2. Therefore, 2 is the GCD of 4, 6. Now let us consider the second example, GCD of 12 and 30. Now let us find out the divisors of 12. The divisors of 12 are 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12 and 12 divides 12. So the divisors of 12 are 1, 2, 3, 4, 6 and 12. Then the divisors of 30 are 1, 2, 3, 5, 6, 10, 15 and 30. So here you can observe that there are common divisors of both 12 and 30 are, I think one is the common divisors of 12 and 30, 2 is also, 3 is also, and 6 is also. So 1, 2, 3 and 6 are the common divisors of both 12 and 30. So in this case you can observe that 6 is the greatest common divisors of both 12 and 30. Therefore GCD of 12, 30 is equal to 6. Let us consider the third example. GCD of 3, 8. The divisors of 3 are 1 and 3. The divisors of 8 are 1, 2, 4 and 8. Here, so common divisors of both 3 and 8 are 1, which is the greatest common divisor. So therefore, so GCD of 3, 8 is equal to 1. Similarly, GCD of minus 12, 30 and 6, GCD of 8, 17, that is equal to 1. GCD of minus 5 is equal to 5. GCD of minus 8, 36 is equal to 4. GCD of 4, 100 is equal to 4. Now we'll move to the theorem. Let A and B be given non-zero integers. There exist integers x and y such that GCD of A, B is equal to ax plus by. Now let us move to the proof of the result. Consider the set S of all positive linear combinations of A and B, that is set S is equal to AU plus BV, such that AU plus BV is greater than 0 and UV belongs to the integers. U and V are integers. Now we prove that S is non-empty. For simplicity, let us assume that let us assume that a is not equal to 0. Then modulus of a is positive, and modulus of a can be written as linear combination, that is a into u plus b into 0 belongs to the set S, because set S contains the linear combination of a and b, where we take either u is equal to plus 1 or minus 1 according as a is positive or negative. Thus S is non-empty. Now, by the definition of well ordering principle, the set S must contain, since D belongs to the set S, then D can be written as linear combination of two integers a and b for some integers x and y. We got as equation 1. Now we claim that D is equal to GCD of a comma b. Now by using division algorithm for a and d, there exist unique integers q and r such that a is equal to d into q plus r, 0 less than or equal to r less than d, that equation 2. Then r can be written as a minus d into q. This is equal to a minus q into, where d using equation 1, that is ax plus by. So this is equal to a minus q into ax minus q into by. This can be written as a is common in the first two terms, 1 minus q into x plus b into minus q into y. So this is of the form a into x1 plus b into y1, where x1 is equal to 1 minus q into x and y1 is equal to minus qy. Again, the equation is correct as equation number 3. If r is positive, then from 3 r is a element of S, because R is also can be written as linear combination of two integers a and b, and from equation 2 R is less than D. This is a contradiction to fact that D is the smallest integer in the set S. Therefore, R is not a greater than 0. Hence, R is equal to 0. So, from equation 2, A is equal to D into 2 plus 0. So, if D divides A by similar reasoning, we can prove that D divides B also. Thus, D is a common divisor of integers A and B. Now let us claim that D is the greatest common divisor. Now, if C divides A and C divides B, then C divides AX plus BY also. That is, C divides D. Since D is a linear combination of X plus BY. That is from 1. So this implies C divides D. This implies modulus of C less than or equal to modulus of D. So this implies C is less than or equal to D. Since D is positive. So now, thus, by the definition of greatest common divisors, it follows that GCD of A comma B is equal to D. So this implies GCD of A comma B is equal to AX plus BY, where D is equal to X plus BY. So this proves the theorem. Let us take corollary. If A and B are given integers, not both 0, then the set S or and set T containing the linear combination of two integers a and b, that is x plus by, such that x and y are integers, is precisely the set of all multiples of d. So where d is equal to GCD of a comma b.